Welcome to Learning PyTorch from Basics to Advanced 2024. Hi, I'm Vivin Arana and I'll be walking you through this course. What will we cover here? We'll start with the beginners level where we're going to go over introduction to PyTorch, getting started with PyTorch, then we'll dive into working with tensors, then autograd and dynamic computational graphs. Then we'll look at building simple neural networks. From there, we'll look at loading and pre-processing data. And finally, we'll look at model evaluation and validation. Once we're comfortable with this beginner level, we're going to jump into the intermediate level section, where we will first look at advanced neural network architectures. Then we'll look at transfer learning and fine-tuning. Following that, we'll cover handling complex data, then model deployment and production, and then debugging and troubleshooting. And again, once you're comfortable with intermediate level, you can dive into advanced level where we will cover distributed training and performance optimization, followed by custom layers and loss functions, then research oriented techniques, followed by integration with other libraries, and finally how you can contribute to PyTorch and community engagement. Welcome to Learning PyTorch from Basics to Advanced 2024. So let's get started. Let's look at Introduction to PyTorch. PyTorch has rapidly become one of the most popular deep learning frameworks in the world. It was developed by Facebook's AI Research Lab. It provides an intuitive and flexible platform for researchers and developers to build, train, and deploy neural networks with ease. Whether you are an academic looking to push the boundaries of machine learning research or a developer aiming to integrate state of the art AI into production systems, PyTorch offers the tools and community support needed to achieve your goals. In this particular section, we will dive into the core concepts of PyTorch, exploring what makes it unique, how it compares to other frameworks, and its evolution over time. By the end of this section, you'll have a solid understanding of PyTorch foundations, setting the stage for deeper exploration into its more advanced capabilities. What is PyTorch? PyTorch is an open source deep learning framework that enables you to build and train neural networks with flexibility and ease. It is designed to accelerate the process of prototyping, building, and deploying machine learning models, especially in the fields of computer vision and natural language processing (NLP). Unlike traditional machine learning libraries that rely on static computational graphs, PyTorch uses dynamic computational graphs, allowing developers to modify the graph on the fly. This makes it particularly suited for research purposes where experimentation and rapid iterations are key. Some of the key points to consider here are dynamic computational graph. So PyTorch allows for flexible model building where graphs are built as the operations are defined, enabling real-time debugging and experimentation. Pythonic nature. PyTorch integrates seamlessly with Python, allowing developers to leverage the extensive Python ecosystem and write code that feels natural and intuitive. Tensors. At its core, PyTorch operates on tensors, which are multidimensional arrays similar to NumPy arrays but with additional capabilities for GPU acceleration. Autograd. PyTorch's automatic differentiation engine, Autograd, enables efficient computations of gradients, which is essential for training deep learning modules using backpropagation. Let's look at the key features and advantages. PyTorch stands out in the crowded field of deep learning frameworks due to several key features and advantages that make it the preferred choice for many researchers and practitioners. First, dynamic versus static graphs. Dynamic graphs. Unlike TensorFlow's static computational graph approach prior to TensorFlow 2.0, PyTorch's dynamic graphs are more flexible and easier to debug. This is particularly beneficial during the research phase where models are often changed frequently. Ease of use. PyTorch's design philosophy emphasizes simplicity and ease of use, making it accessible to beginners while still powerful enough for advanced users. Seamless integration with Python. Pythonic syntax. Python's syntax is intuitive. PyTorch's syntax is intuitive and closely mirrors standard Python code, reducing the learning curve and allowing for easy integration with Python libraries like NumPy and SciPy. Community support. PyTorch has a large and active community which contributes to a wealth of tutorials, documentation, and third-party libraries that can accelerate development. GPU acceleration. Efficient computation. PyTorch supports seamless execution of GPUs, significantly speeding up the training process of large models. With just a few lines of code, you can move your models and data to GPU, harnessing the power of modern hardware. Robust ecosystem. It has libraries and extensions. PyTorch offers a range of libraries and tools such as Torch Vision for computer vision, Torch Text for NLP, and Torch Serve for model deployment that make it a comprehensive framework for various applications. Research and production. PyTorch strikes a balance between being a research friendly platform and a robust production ready framework. This dual nature makes it versatile and widely adopted across academia and industry. Let's look at PyTorch versus other frameworks. Now, PyTorch is often compared to other deep learning frameworks, each with its strengths and trade offs. In this subsection, we'll compare PyTorch with TensorFlow, Keras, and other popular frameworks. Now, its comparison with TensorFlow. Graph construction. PyTorch uses dynamic graphs, allowing on the fly changes, while TensorFlow traditionally used static graphs, which can be less intuitive but offer optimization benefits. This was before 2.0, where it introduced eager execution to bridge this gap. Learning curve. PyTorch is often praised for its ease of use and intuitive syntax, making it more beginner friendly compared to the more complex TensorFlow. Community and ecosystem. TensorFlow has a larger ecosystem and more tools for production deployment, but PyTorch growing community and native integration with Python make it a strong contender. PyTorch versus Keras. Flexibility. Keras, being a high-level API, is simpler and more abstract, which can be an advantage for quick prototyping but may limit flexibility. PyTorch, with its low-level approach, offers more control over the model building process. Performance. PyTorch generally provides better performance, especially for research purposes, due to its fine-grained control over computations. PyTorch versus other frameworks. MXNet. MXNet offers a blend of dynamic and static graphs but is less popular and lacks the extensive community support that PyTorch enjoys. Chainer. Chainer, like PyTorch, uses dynamic graphs but has a smaller community and ecosystem. Let's look at the history and development of PyTorch. Understanding the history of PyTorch provides insights into its design choices and why it has become so popular in the AI community. Origins. Now, developed by Facebook's AI research, which is FAIR, PyTorch was created by FAIR in 2016 as an evolution of the Torch library, which was primarily used in the Lua programming language. The shift to Python was motivated by the need for a more widely adopted and flexible language. Some of the key milestones in its history are PyTorch 1.0, which was in 2018, marked the merging of PyTorch and Cafe 2, bringing together the flexibility of PyTorch with the production capabilities of Cafe 2, marking PyTorch more suitable for both research and deployment. Growing adoption. Over the years, PyTorch has seen exponential growth in adoption, especially in academic research, due to its ease of use and dynamic nature. Recent developments. The introduction to PyTorch XLA for TPU support and the PyTorch Lightning library for simplifying model training has further solidified PyTorch's position as a leading framework. Community and ecosystem. Community contributions. PyTorch has a vibrant community that actively contributes to its development, leading to continuous improvements and the rapid addition of new tasks. Industry adoption. PyTorch's adoption in the industry has grown, with companies like Facebook, Microsoft, and Tesla using it in production environments. Getting started with PyTorch. So, before diving into deep learning models and complex neural networks, it's crucial to ensure you have PyTorch installed and ready to use in your development environment. In this section, we will guide you through the installation process of PyTorch using pip and conda, how to set up a robust development environment and run your first PyTorch program. By the end of this section, you will have a functioning setup that allows you to start experimenting with the core features of PyTorch. So, installing via pip or conda. Installing PyTorch is straightforward process, and depending on your preference, you can either use pip, which is Python's package installer, or conda, the package and environment manager from Anaconda. Installing using pip. If you're using pip as your package manager, PyTorch can be installed by simply executing the following command in your terminal or command prompt, which is pip install torch, torch vision, and torch audio. This command installs three components: torch, the core PyTorch library; torch vision, a library that provides popular data sets, model architectures, and image transformations for computer vision tasks; and then torch audio, a library for audio processing tasks. Installing using conda. If you prefer using conda, especially useful if you are working within the Anaconda ecosystem, you can install PyTorch by specifying the correct version for your system by saying conda install PyTorch, torch vision, torch audio -c PyTorch. This command uses the official PyTorch channel on conda to ensure you get the correct versions of PyTorch and related libraries. Installing with CUDA for GPU acceleration. PyTorch can leverage GPU acceleration through NVIDIA's CUDA platform. If you have an NVIDIA GPU and the necessary drivers installed, you can install PyTorch with GPU support. For pip, you can say pip install torch, torch vision, torch audio --index -url and give the URL https://download.pytorch.org/whl/cu118. And for conda install PyTorch, torch vision, torch audio, PyTorch-CUDA 11.8-c PyTorch-c NVIDIA. Now make sure to replace the CUDA version 11.8 with the version compatible with your system. Setting up a development environment. To effectively work with Python, it is essential to set up a development environment that supports efficient coding, debugging, and testing of your models. In this subsection, we will guide you through the process of setting up such an environment. Now, first, choosing a code editor or IDE. Several development environments are commonly used with PyTorch, and each has its pros and cons. Some popular options include first one, VS Code, Visual Studio Code, which is what I use, a lightweight but powerful code editor with great support for Python and Jupyter notebooks. It also has useful extensions for PyTorch development, such as the PyTorch snippets extension. Jupyter notebooks, ideal for interactive development, allowing you to run code cells independently and visualize outputs, which is perfect for testing small snippets of PyTorch code. PyCharm, a robust IDE for Python development with excellent code navigation, debugging tools, and virtual environment support. Setting up the virtual environments. It's a good practice to create isolated virtual environments for your PyTorch projects to avoid conflicts with other Python packages. Depending on your package manager, you can set up a virtual environment as follows. First, using V environment, which stands for virtual environment, is Python's built-in virtual environment tool. You can say python-m venv pytorch_environment, which is the name that you can give. Source pytorch_env/bin/activate is on Windows you'll use PyTorch underscore env slash script slash activate. Now using conda, you can say conda create dash n PyTorch underscore env python equal to 3.10, which is the version. Conda activate PyTorch env. After activating the virtual environment, you can install PyTorch as described earlier. Installing essential development tools. To enhance your development workflow, it's helpful to install additional tools such as Jupyter Notebook. For interactive coding, you can say pip install notebook. Matplotlib for plotting and visualization data. Pip install matplotlib, which you probably already have if you're using Python. And then IPython for a more powerful interactive Python shell. You can say pip install IPython. These tools help you write, test, and visualize your PyTorch code efficiently. Run your first PyTorch program. Now that you have PyTorch installed and your environment is set up, it's time to write and run your first PyTorch program. In this subsection, we will walk through a simple program that demonstrates some core PyTorch concepts, including tensor creation and basic operations. Creating a simple PyTorch program. Open your preferred code editor or Jupyter Notebook and create a new Python file, example first underscore PyTorch underscore program.py. Here's a simple PyTorch program that demonstrates how to create a tensor, perform a matrix multiplication, and display the result. So in the first line, you'll say import torch. Then I've added a comment, say create two random tensors. Tensor A, which is torch.rand 3,3, tensor B, torch rand 3,3. This is for randomly creating tensors. Next, result equal to torch.matmul tensor A and tensor B, which perform the matrix multiplication. That's why the name matmul. Print the tensors and the result by saying print using the print command tensor A and print tensor A value. And then again the string tensor B separated by in the next line tensor B, and then result of the matrix multiplication by saying print result. Now how to run the program? To run the program, simply execute the Python file in your terminal or using the run functionality of your IDE. If you're using Jupyter Notebooks, execute the code cell. If everything is set up correctly, you should see the output similar to the following. Tensor A, where you'll see the tensor with random 3x3 matrix, tensor B with random 3x3 matrix, and the result of the matrix multiplication, which is also 3x3 matrix with the multiplication result. If you have any issues or problems while doing this, please leave it in the comments and I'll get back to you as soon as possible. Now exploring further, to take it a step further, try creating a different type of tensors such as zeros, ones, or random tensors, performing element-wise operations and moving tensors to the GPU if available. Here's an example of moving a tensor to a GPU, where if torch.cuda is available, saying tensor A equal to tensor.a.to CUDA, then same for tensor B, and then the result torch matmul with the same one tensor A, tensor B, and you can print out the result. This will utilize the GPU for computations, which can significantly speed up training for larger models. So you can play with it just to see if it's available. Now working with tensors. Tensors are fundamental building blocks in PyTorch, much like arrays in NumPy, but with additional capabilities tailored for deep learning. Understanding how to work with tensors is crucial as they are used to represent inputs, outputs, weights, and everything in between in a neural network. In this section, we will dive deep into the concept of tensors, exploring their structure, how to create them, and the various operations you can perform on them. By the end of this section, you will have a strong grasp of how to manipulate tensors, which is essential for building and optimizing deep learning models. So understanding tensors, there's three things: rank, shape, and data type that we'll go over. Before diving into tensor creation and operations, it's important to understand the basic attributes of tensors, again, which are rank, shape, and data type. Rank, or also called as dimensionality, the definition of that is the rank of a tensor refers to the number of dimensions it has. For example, a scalar is a tensor with rank 0. A vector is a rank 1 a matrix is a rank 2, and so on. So here is an example. Rank 0 is a scalar, which is 3. Rank 1, which is a vector, which is an array of 1, 2, 3. And rank 2, which is a matrix, example, a array of arrays 1, 2, 3, and 4, 5, 6. Higher ranks. Tensors can have higher ranks, which is 3D, 4D, etc., depending on the application. Example, 3D tensors for RGB images, 4D tensors for batches of images. Shape. The shape of a tensor is a tuple that gives the size of each dimension. For example, a 2D tensor with the shape 3, 4 represents a matrix with 3 rows and 4 columns. Example, a tensor with shape 2, 3, 4 would have two matrices of shape 3, 4 stacked together. Data type. Tensors can store data of different types such as integers, floats, or booleans. The data type is important for precision and memory usage. Common data types are torch.float32, torch.int64, and torch.bool. Here's an example. A tensor with d type equal to torch float32 would store 32-bit floating point numbers. Understanding these attributes is crucial because they determine how tensors are stored in memory and how operations are applied to them. Creating tensors from data. Tensors can be created in various ways depending on the data you have and the requirements of your model. In this subsection, we will cover the most common methods to create tensors. Creating tensors from lists or arrays. From list, let's see how we can do this. You can easily convert Python list or the nested list into PyTorch tensors using the torch.tensor function. Here's an example. Import torch and then you can say tensors from list variable which say stores torch.tensor from an array 1, 2, 3 or from a list. From NumPy arrays. Tensors can also be created from NumPy arrays, which is useful if you are transitioning from a NumPy based code base. Here is an example where I am importing the NumPy library first as np and then NumPy array equal to np.array where I am adding an array of arrays 1, 2, 3 and 4, 5, 6 into a bigger array. So it's a matrix. Now tensor from NumPy equal to torch.tensor NumPy array. Creating tensors with specific values, zeros and ones. PyTorch provides a function to create a tensors filled with zeros or ones, which are often used for initialization purposes. Here is an example. You have a variable tensor zeros where I am assigning torch.zeros 3 by 3. So it creates a 3 by 3 tensor and assigns it to zeros. And then I have tensor ones, which is torch.ones with a 2 by 2. Random tensors. Random tensors are commonly used for initializing weights in neural networks. Example, random tensor equal to torch.rand 4, 4, where uniform distribution between 0 and 1. Normal tensor torch.randn 4, 4, where is normal distribution with a mean 0 and a variance of 1. Specifying data types and devices. For data type, when creating a tensor, you can specify its data type using the dtype argument. Here is an example. Float tensor equal to torch.tensor 1.0, 2.0, 3.0 and the second attribute is the data type where dtype equal to torch.float32. Device or GPU/CPU. Tensors can be created directly on a GPU if available, which is crucial for performance in deep learning tasks. GPU tensor equal to torch.tensor where I create the item 1, 2, 3 and then I'm just saying device equal to CUDA. Tensor operations, arithmetic, indexing and slicing. Once tensors are created, various operations can be performed on them. This subsection covers the basic of arithmetic operations, indexing and slicing, which are essential for manipulating and extracting data from tensors. Let's look at arithmetic operations. Element-wise operations. PyTorch supports element-wise arithmetic operations such as addition, subtraction, multiplication, and division. Here is an example. Tensor A equal to torch.tensor 1 to 3 and tensor B equal to torch.tensor 4, 5, 6. Now sum of this tensor equal to tensor underscore A plus tensor underscore B, which is element-wise addition. Matrix multiplication. Matrix multiplication is a key operation in neural networks and can be performed using torch.matmul or the @ operator. Here is an example. Matrix A equal to torch.tensor 1, 2 and 3, 4. Matrix B equal to torch.tensor 5, 6 and 7, 8. Result equal to torch.matmul matrix underscore A comma matrix underscore B. Indexing. Single element access. Similar to Python list or NumPy arrays, you can access individual elements of a tensor using square brackets. Example, tensor equal to torch.tensor 1, 2 and 3, 4. Now element equal to tensor 0, 1, which accesses the element at row 0, column 1. Slicing. Subtensors. You can extract subtensors by specifying ranges of indices similar to slicing in Python. So if you have a tensor torch.tensor 1, 2, 3, 4, 5, 6 and 7, 8, 9, 3 different lists, subtensor equal to tensor, I'm saying colon, comma 1 colon 3, which extract columns 1 and 2 from all rows. Advanced indexing. PyTorch also supports advanced indexing, such as selecting specific rows or columns using lists of indices. Example, saying tensor torch.tensor 1, 2, 3, 4 and 5, 6. Now selected rows equal to tensor 0, 2 and colon. Select the first and the last row in this particular case because I am saying 0 and 2. Broadcasting and in-place operations. In this subsection, we'll explore more advanced tensor operations, including broadcasting, which allows for efficient computation with tensors of different shapes, and in-place operations, which modify tensors without creating new ones. Let's look at broadcasting. Broadcasting is a technique used by PyTorch to perform operations on tensors of different shapes. The smaller tensor is broadcast across the larger tensor so that they have compatible shapes for element-wise operations. Here is an example. Torch.tensor 1, 2, 3 and 4, 5, 6 for tensor A. For tensor B, we have torch.tensor 1, 2, 3. Result equal to tensor underscore A plus tensor underscore B. Now in this case, tensor B is broadcasted to match the shape of tensor A. Now the rules include broadcasting follows specific rules regarding dimension matching. Understanding these rules is crucial for avoiding shape mismatches and ensuring efficient computation. In-place operations. In-place operations modify the content of a tensor without allocating new memory, which can be more efficient but should be used cautiously to avoid unintended side effects. Notation is in PyTorch, in-place operations are typically denoted by a trailing underscore. Example, a add underscore and the function. Here is an example. Tensor torch.tensor 1, 2, 3 tensor.add underscore 5. It adds 5 to each element in place, modifying the original tensor. Use cases. In place operations are useful in scenarios where memory efficiency is crucial, but they can lead to bugs if the original tensor is needed elsewhere in its original state. Autograd and dynamic computation graphs. One of the core features that makes PyTorch a powerful framework for deep learning is its ability to automatically compute gradients. This is facilitated by PyTorch's Autograd module, which enables automatic differentiation essential for optimizing neural networks. Additionally, PyTorch's dynamic computation graphs allow for a more flexible and intuitive way to build and modify models on the fly. In this section, we will explore these features in detail, providing you with a deep understanding of how PyTorch handles gradient computation and why dynamic computation graphs are a game changer for deep learning research and development. Let's go over the introduction of AutoGrad. The AutoGrad module is at the heart of PyTorch's capability to automatically compute gradients for tensor operations. Gradients are essential in the optimization of neural networks as they provide the necessary information to update model parameters during training. What is AutoGrad? AutoGrad is PyTorch's automatic differentiation engine that records operations performed on tensors to create a computation graph. This graph is used to calculate gradients during backpropagation. What is the importance of it? Gradients are used to optimize the loss function, guiding the model in the right direction during training. How AutoGrad works? First, using computation graph. When you perform operations on tensors, PyTorch dynamically constructs a computation graph that tracks the dependencies between tensors. The backward pass. During the backward pass, AutoGrad traverses this graph to compute gradients for each tensor involved in the operations. Key concepts requires grad. By default, PyTorch does not compute gradients for tensors. To enable gradient computation, you must set requires grad to true when creating a tensor. Here is an example where I am saying x equal to torch.tensor 1.0, 2.0, 3.0, and in the second attribute I am saying requires grad equal to true. Gradients. Once gradients are computed, they are stored in the .grad attribute of the tensor. Automatic differentiation with torch.autograd. In this video, we will delve deeper into how to use the torch.autograd module to perform automatic differentiation, which is essential for training deep learning models. Computing gradients. Backward method. After performing some operations on a tensor, you can compute the gradient by calling the backward method on the result. Here is an example, y equal to x times 2, which is an example operation. Then y.sum dot backward, which computes gradients, print x.grad, which will output the gradients in there. Now the gradient accumulation. Gradients are accumulated into the .grad attribute by default, which means that calling backward multiple times without resetting gradients can lead to incorrect results. You can reset gradients using 0_grad function. Gradient descent. For optimization, the gradients computed by AutoGrad are used to update model parameters using an optimization algorithm such as gradient descent. Here is an example with torch.noGrad function, x minus equal to learning rate times x.grad. Detecting tensors. Sometimes you may need to detach a tensor from the computational graph to stop it from tracking gradients. This can be done using the detach method. Here is an example, detach tensor equal to x.detach. Higher order gradients. Support for higher order gradients. PyTorch also supports higher order gradients which are necessary for certain advanced techniques like meta learning. Example is x equal to torch.tensor 1.0, 2.0, 3.0 requires grad equal to true, and I am saying y equal to x star star 2 grad outputs equal to torch dot once underscore like function with parameter x, gradients equal to torch dot autograd grad, parameters are y, x, grad outputs equal to grad outputs, and create graph equal to true. Dynamic computation graphs in PyTorch. One of the key differences between PyTorch and other deep learning frameworks like TensorFlow pre 2.0 is the use of dynamic computational graphs. This subsection explores how these graphs work and why they are advantageous. What are dynamic computation graphs? Dynamic computation graphs, also known as defined by run graphs, are built on the fly as operations are executed. Unlike static graphs, which are defined before running the model, dynamic graphs allow you to modify the graph structure during runtime. Flexibility. This feature provides greater flexibility, especially in research and experimentation where model architectures may need to be adjusted frequently. What are the advantages of dynamic computational graph? First one, ease of use. The defined by run approach makes the code more intuitive and closer to standard Python code, reducing the learning curve for new users. Debugging. Dynamic graphs are easier to debug because they are built step by step, allowing for the use of standard Python debugging tools. Conditionals and loops. PyTorch's dynamic graphs support conditionals and loops naturally, making it easier to implement complex model architectures such as RNNs and recursive models. Practical example of dynamic graphs. Examples: consider a model where the number of layers is determined by an external condition such as the length of an input sequence. With dynamic computational graph, you can easily adjust the number of layers based on the runtime conditions. Here is an example: layers equal to empty array for I in range num underscore layers dot append torch.nn linear 10 comma 10, x equal to torch dot random 1 comma 10, and for layers in layers x equal to torch dot relu layers x. This approach allows you to build and modify models in a more natural and flexible way, accommodating the needs of modern deep learning research and applications. Building simple neural networks. Neural networks are the backbone of modern deep learning. They consist of layers of interconnected neurons, which are designed to automatically learn patterns from data. Building and training neural networks is a core skill in deep learning, and PyTorch makes it straightforward with its modular design. In this section, we will explore the fundamental components of a neural network, how to construct neural networks using PyTorch's torch.nn.module, and the essential steps involved in training them. We will also cover the crucial concepts of loss functions and optimizers, which play a key role in the learning process. Anatomy of a neural network. To build and understand neural networks, it's important to grasp their basic structure and how the different components interact with each other. Let's look into neurons and layers. Neurons, the basic building blocks of a neural network, are neurons, which are analogous to the biological neurons in the brain. Each neuron that takes inputs processes them and produces an output. In mathematical terms, a neuron performs a weighted sum of its inputs, applies an activation function, and produces an output. A single neuron might calculate the following: y equal to sigma of w1 x1 plus w2 plus x2 plus b, where sigma is an activation function like ReLU or sigmoid. W1, W2 are weights, x1, x2 are inputs, and b is the bias. Layers. Neurons are grouped into layers. A typical neuron network has an input layer, one or more hidden layers, and an output layer. The input layer receives the input data. The hidden layers perform computations and extract features. These layers can vary in number and size depending on the complexity of the task. The output layer produces the final output of the network, such as class scores in a classification task. Forward pass. The forward pass is the process where input data is passed through the network layer by layer, producing an output. This output is then compared with the ground truth to calculate the loss. Activation functions. The role is activation functions introduce non-linearity into the model, allowing the network to learn complex patterns. Common activation functions include ReLU, which is rectified linear unit. The most popular activation function defined as ReLU x equal to max of 0, x. Sigmoid, used in binary classification problems, defined as sigma of x equal to 1 by 1 plus e raised to minus x. Then we have tan h, another activation function that outputs values between minus 1 and 1, defined as tan h of x equal to e raised to x minus e raised to minus x upon e raised to x plus e raised to minus x. Creating neural networks with torch.nn module. PyTorch provides the torch.nn module class, which is a base class for all neural network modules. It's designed to encapsulate the structure and behavior of neural networks. Defining a neural network class. First, subclassing torch.nn.module. To define a neural network in PyTorch, you create a class that inherits from torch.nn.module. This class must implement two methods: init to define the network's layers and forward function to define how the input data flows through the network. Here's an example. Import torch and then import torch.nn as nn. I'm creating a class simple nn with attribute nn.module, and first function is a def init with self inside the arguments, super simple nn comma self dot init. So I'm calling the super function here. Then I'm saying self dot fc1 equal to nn dot linear 10 comma 50, which is the first fully connected layer. Then I'm saying self dot fc2 equal to nn dot linear 50 comma 1, which is the output layer. Then I have another function here, forward self and x arguments, x equal to torch dot relu self dot fc1 with x, where apply the relu activation after the first layer, and then x equal to self dot fc2 of x, which is the output layer, and return x. Initializing and using the network. Instantiation. Once the network class is defined, you can instantiate it and pass data through it. Here is an example. Model equal to simple nn, and then input data equal to torch.random with 1 and 10, which random input tensor with 10 features, and output equal to model input underscore data, and the print output. Now the parameters of the model, such as weights and biases, are automatically registered and can be accessed using model.parameters. Managing the complexity. Modular design. PyTorch encourages modular design where complex networks are composed of smaller reusable modules. For example, you can create custom layers by combining existing layers or by defining new layers that inherit from the torch.nn.module. Training a neural network, forward pass and backward pass. Now, training a neural network involves a cycle of forward and backward passes followed by updates to the model's parameters. Forward pass involves passing the input data through the network to obtain predictions. This is the first step in the training process and is used to compute the loss. Backward pass, which is also called as back propagation. The backward pass involves computing the gradients of the loss with respect to each parameter of the network using back propagation. This is done by calling the backward method on the loss. Here is an example, loss.backward, which computes the gradients for each parameter. Gradient descent. The gradients are then used to update the model's parameters in the direction that reduces the loss, typically using an optimizer. Epochs and iterations. Epoch is one complete pass through the entire training dataset. An iteration is one pass through a single batch of data. The number of iterations per epoch depends on the batch size and the size of the dataset. Loss functions and optimizers in PyTorch. Loss functions and optimizers are key components in the training process. The loss function quantifies how well the model's predictions match the target values, while the optimizer updates the model's parameters to minimize this loss. Loss function. A loss function measures the difference between the network's predictions and the actual targets. PyTorch provides several loss functions for different types of tasks. MSE loss, mean squared error. used for regression tasks where the goal is to predict continuous values. Example is loss fn equal to nn dot msc loss equal to loss underscore fn, predictions and targets. Cross entropy loss, commonly used in classification tasks where the target is a category. Example is loss fn equal to nn dot cross entropy loss and loss equal to loss function, predictions and targets. Optimizers. An optimizer updates the network's parameters based on the computed gradients. PyTorch provides several optimizers including SGD, which is the stochastic gradient descent, the most basic optimizer that updates parameters by moving them in the direction of the negative gradient. Here is an example optimizer where torch.optim.sgd model.parameters and LR equal to 0.01. Adam, an advanced optimizer that adapts the learning rate for each parameter, often leading to faster convergence. Here is an example of an optimizer equal to torch.optim.adam model.parameters LR equal to 0.001. Optimizers. Optimization loop. In step 1, say zero the gradients to prevent gradient accumulation, which is look in the example below, it says optimizer.zero grad. Then step 2, perform the forward pass and compute the loss. As in the example, you'll see output equal to model input data. Step 3 is perform the backward pass to compute gradients, where in the example you'll see loss.backward function is what I'm calling. And step 4 is update the parameters using the optimizer, where you say optimizer.step. Loading and pre-processing data. Data is the fuel that powers neural networks. However, raw data is often messy and unstructured, requiring careful pre-processing before it can be fed into a model. PyTorch provides powerful tools for loading and pre-processing data, making it easier to manage large data sets and perform necessary transformations. In this section, we will explore how to efficiently load data using torchvision.datasets and torch.utils.data.dataset. Apply common pre-processing techniques such as normalization and resizing, create custom datasets, and handle batch processing. By the end of this section, you will be well equipped to manage and pre-process data for your deep learning projects. Loading data with torchvision.datasets and torch.utils.data.dataset. One of the most important tasks in deep learning is efficiently loading and managing data. PyTorch provides two essential tools for this. One is that torchvision.datasets for standard datasets and torch.utils.data.dataset for custom datasets. Let's look at loading standard datasets with torchvision.datasets. Torchvision.datasets provides access to popular datasets such as MNIST, Cipher10, and ImageNet, which are commonly used for training and benchmarking deep learning models. Here is an example. Import torchvision.datasets as datasets, and from torchvision.transformers import 2tensor. And then I'm loading the MNIST dataset by saying creating a variable MNIST train equal to datasets.mnist root equal to data train true transform 2tensor function and download equal to true. Then I am creating the MNIST test variable where datasets equal dot MNIST root data train false transform 2tensor and download equal to true. Transformations. The transform argument allows you to apply pre-processing steps like converting images to tensors, normalizing pixel values, and more. Custom datasets with torch.utils.data.dataset. Now, when working with datasets that are not available in torchvision.datasets, you can create your own dataset class by subclassing torch.utils.data.dataset. Now, there are three steps to creating a custom dataset. Step 1 is subclass the torch.utils.data.dataset. Step 2 is implement the underscore len underscore function method to return the number of samples in the dataset. And step 3 is to implement the getItem method to load the and return a sample from the dataset at the given index. Here is an example where I'm import torch, then from torch.utils.data I'm importing dataset. Then I'm creating a class custom dataset with dataset passed to it, and the first function inside the initialization function where I am passing self, data, labels and transform equal to none, and inside that I'm setting self.data to data, self.labels to labels and self.transform to transform. Then another function len and passing self to it, and I'm returning length of self.data. Then I'm creating the get item, which is the third step, where I'm passing self and idx, and I'm creating a variable sample equal to self.data idx and label equal to self.labels of idx. If self.transform, I have sample equal to self.transform sample, and then finally returning the sample and label. Pre-processing techniques: there's normalization, resizing and transformations. Pre-processing is a crucial step that can significantly impact the performance of your model. Common techniques include normalization, resizing, and other transformations that prepare data for training. Let's look at normalization first. Normalization involves scaling the input data to a specific range, typically 0 to 1 or -1, 1. This helps in speeding up the training process and can lead to better convergence. Here is an example. From torchvision.transforms import normalize, and now we normalize images with mean and std by saying transform equal to normalize, mean equal to 0.5 and std equal to 0.5. Resizing. Definition is resizing images to a fixed size is necessary when working with neural networks, as they often expect input images to have same dimensions. Here is an example. From torchvision.transforms I'm importing resize, and I'm resizing images to 28 by 28 pixel by saying resize 2828 and assigning it to transform variable. Transformations. PyTorch torchvision.transforms module provides a variety of transformations that can be applied to images, including random cropping, flipping, rotation and more. Here is an example. From torchvision.transform I'm importing compose, random horizontal flip and two tensor. Now I'm composing a multiple transformations here by calling the compose function and assigning it to transform, where inside that I'm saying resize 28 by 28, random horizontal flip function and two tensor function. Custom data sets and data loaders. When working with data sets that are not pre-processed or require custom handling, you can create custom data sets and data loaders. Custom dataset implementation. First, data organization. Custom datasets often involve loading data from various sources such as images, text files, or even databases. Organizing and handling these data efficiently is key. First, import OS. From PIL, import the image, and I'm creating a class image dataset here with passing the dataset, and I'm creating first function initialization, which is passing self image directory and transform equal to none. I'm setting the self.image directory equal to image directory, self equal to image dot file names equal to os dot list directory image directory, self dot transform equal to transform. Then I'm creating the length function with self in passed to it, and I'm returning length of self dot image file names. Then finally the get item function self and idx, the image name equal to os dot path dot join self image directory self image file names with idx, image equal to image dot open image name, and if self dot transform image equal to self dot transform image, and return the image back. Data loaders. Data loaders are used to load data in batches, shuffle the data, and handle parallel data loading using multiple workers. Here is an example. From torch.utils.data import the data loader, and then create a data loader for the custom dataset. Create a variable custom dataset and set an image dataset image underscore dir equal to part2 images, and transform equal to 2 tensor function. Then data loader equal to data loader function, custom data set that we created previously, batch underscore size equal to 32, shuffle true, and number of workers equal to 4. The advantages is using data loaders improves the efficiency of the training process, especially when working with large data sets. Batch processing and iterating over datasets. Batch processing is essential for training neural network efficiently, allowing models to process multiple samples at once. Batching with data loaders. Batching involves dividing the dataset into smaller, manageable chunks called batches. This reduces the computational load and allows for more stable training. Example is data loader equal to data loader and past dataset, batch size 24 and shuffle equal to true. Iterating over batches. Looping through data. In the training loop, you typically iterate over the dataset in batches. Each iteration processes one batch of data. Here is an example. For batch in data loader, inputs labels equal to batch. Forward pass, backward pass, and optimization steps go after that. Performance consideration. First one is data parallelism. If your system has multiple GPUs, you can leverage data parallelism to distribute batches across GPUs, speeding up the training process. Optimizing data loading. Using multiple workers in the data loader num underscore workers can significantly reduce the time spent on loading data as it allows for parallel data loading. Model evaluation and validation. Evaluating and validating a model is a critical step in the machine learning process, as it ensures that the model not only performs well on the training data but also generalizes to unseen data. This section covers the essential concepts and techniques needed to evaluate and validate machine learning models effectively. We'll explore various evaluation metrics such as accuracy, precision, and recall, discuss common validation techniques, and provide strategies for monitoring model performance during training. Additionally, we'll address how to handle overfitting and underfitting, two common challenges in model training. Understanding evaluation metrics, accuracy, precision, and recall. Evaluation metrics are used to quantify the performance of a model. Different metrics are suited for different types of problems, such as classification or regression. Accuracy. Accuracy is the ratio of correctly predicted instances to the total instances. It is commonly used metric for classification problems where the classes are balanced. Here is the formula. Accuracy equal to number of correct prediction divided by total number of predictions. Example, if a model correctly classifies 90 out of 100 samples, the accuracy is 90%. Limitation. Accuracy can be misleading in cases of imbalanced datasets where one class significantly outnumbers the other. Precision. Precision measures the accuracy of the positive predictions made by the model. It is particularly useful when the cost of false positives is high. Formula is precision equal to true positives divided by true positives plus false positives. Example is in a spam detection system, precision would indicate how many of the emails classified as spam were actually spam. Use case. Precision is crucial in scenarios like medical diagnosis where false positives can lead to unnecessary treatments. Recall. Recall, also known as sensitivity or true positive rate, measures the model's ability to correctly identify all positive instances. It is important when the cost of false negatives is high. Formula is recall equal to true positives divided by true positives plus false negatives. Example is in a cancer screening test. Recall would indicate how many of the actual cancer cases were correctly identified. Use case. Recall is vital in applications like disease screening or fraud detection, where missing a positive case could have severe consequences. F1 score. The F1 score is the harmonic mean of precision and recall, providing a balanced measure when both metrics are important. F1 score formula is F1 score equal to 2 times precision times recall divided by precision plus recall. Use case: the F1 score is particularly useful when dealing with imbalanced data sets, offering a single metric that balances precision and recall. Validation techniques: train validation split, k-fold, cross validation. Now, validation techniques are used to assess how well a model generalizes to unseen data. These techniques help prevent overfitting and ensure that the model's performance is not overly optimistic. Let's look at train validation split. The data set is split into two parts, one for the training the model and the other for validating it. A common split ratio is always 80 by 20 or 70-30, depending on the size of the data set. The process is: first step, split the data set into training and validation sets. Step 2 is train the model on the training set. And step 3, evaluate the model on the validation set. Here is an example. From sklearn.model selection, import train test split. Now I'm creating variables xtrain, xval, ytrain and yval. This will be filled out by this function train test split, where I'm passing the x, y, test size equal to 0.2 and random state equal to 42. The advantages is it's simple to implement and computationally efficient. Disadvantages in this case are the model's performance might be sensitive to particular split, especially with small datasets. K-fold cross-validation. The K-fold cross-validation involves dividing the dataset into k equal parts or folds. The model is trained on k1 folds and validated on the remaining fold. This process is repeated k times, with each fold used exactly once as the validation data. Process is 3 steps again. Step 1 is split the dataset into k folds. Step 2 is train the model k times, each time using the different fold as the validation set and the remaining k minus 1 folds as the training set. And step 3 is average the performance across all k runs. Here is an example. From sklearn.model selection, import the cross underscore val underscore score. And from sklearn.ensemble, import random forest classifier. Now I'm creating the model calling the model by calling the random forest classifier function, and the score is equal to cross val score, and I pass the model x, y and cv equal to 5, where cv is the 5-fold cross validation. Advantages of this is provides a more reliable estimate of model performance, especially with small datasets. Disadvantages is computationally expensive, especially for large datasets or complex models. Then there's stratified k-fold, a variation of k-fold cross validation that preserves the percentage of samples for each class, ensuring that each fold is representative of the overall class distribution. Use case is particularly useful in classification tasks with imbalanced datasets. Monitoring model performance during training. It's essential to monitor the model's performance throughout the training process to detect issues such as overfitting or underfitting early. Loss curves. Plotting the training and validation loss as a function of epochs helps in visualizing how well the model is learning. Here is an example where I'm importing matplotlib.pyplot as plt, and from plt I'm calling the plot function and passing train losses label equal to training loss and val losses label equal to validation loss. Then I'm calling the legend function on plot and then finally show. Interpretation. A steady decrease in training loss with a similar trend in validation loss indicates that the model is learning effectively. If the validation loss starts increasing while the training loss continues to decrease, it may indicate overfitting. Monitoring model performance during training using accuracy curves. Similar to loss curves, accuracy curves show how the model's accuracy changes over time for both training and validation datasets. Early stopping. Early stopping is a technique where training is halted once the model's performance on the validation set stops improving. This helps prevent overfitting. Example: implement early stopping by monitoring validation loss and stopping training if it doesn't improve for a certain number of epochs. Handling overfitting and underfitting. Overfitting and underfitting are common challenges in machine learning. Overfitting occurs when a model performs well on training data but poorly on unseen data, while underfitting occurs when the model is too simple to capture the underlying patterns in the data. Understanding overfitting. The symptoms. The model has very low training loss but high validation loss. It captures noise or irrelevant patterns in the training data. Solutions. First one is regularization. Techniques such as L1 or L2 regularization adds a penalty to the loss function, discouraging overly complex models. Here is an example where I have a variable model and I'm calling the torch.nn.linear function and passing in features equal to 10, out features equal to 1. Optimizer variable where I'm saying torch.option optim.hgd, model.parameters lr equal to 0.01 and weight decay equal to 0.01. This is the L2 regularization. Solutions: dropout. Randomly dropping units during training helps prevent the model from relying too heavily on any particular path. Here is an example where I have the dropout layer where I'm calling the dropout function torch.nn.dropout and passing p equal to 0.5. Another solution is data augmentation. Augmenting the training data with various example rotations or flips can help the model generalize better. Here is an example where I am importing random horizontal flip from the torch vision.transforms and I'm creating a variable transform and calling this random horizontal flip with p equal to 0.5. Understanding underfitting. The symptoms are the model has high training and validation loss, indicating that it's too simple to capture the underlying patterns in the data. Solutions are increase the model complexity, add more layers or units to the model to make it more expressive. Train longer. The model may require more epochs to learn the underlying patterns. Reduce the regularization. If regularization is too strong, it might be preventing the model from learning effectively. Advanced neural network architectures. As deep learning evolves, so do the architectures used to solve increasingly complex problems. Traditional feed-forward neural networks are often insufficient for tasks involving image recognition, sequential data, or natural language processing. This section delves into the advanced neural network architectures that have revolutionized these domains. First one is the convolutional neural networks (CNNs) for image data, then recurrent neural networks, which is RNNs, and long short term memory networks, which is LSTMs for sequential data, and transformer networks for tasks requiring attention mechanisms like language modeling. Each of these architectures is designed to address specific challenges and leverage unique capabilities, making them powerful tools in the deep learning toolkit. Let's go over convolutional neural networks or CNNs. Convolutional neural networks (CNNs) have become the go-to architecture for image-related tasks. They are specifically designed to process data with a grid-like topology, such as images, by taking advantage of the spatial structure of the data. Convolutional layers and filters. The convolutional layers, the core building block of CNNs, which applies a set of filters or kernels to the input image. Each filter slides across the input image to produce a feature map highlighting specific patterns such as edges, textures, or colors. Example is a 3 by 3 filter might detect horizontal edges in an image. As it convolves across the image, it creates a new matrix, which is feature map, where the presence of edges is marked. Filters, which are kernels. Filters are small matrices used to detect specific features in the input data. The values in these filters are learned during the training process. Stride and paddling. Stride determines how much of the filter moves at each step, and paddling is used to maintain the original dimensions of the input after convolution. Pooling layers. Max pooling, average pooling. Pooling layers are used to reduce the spatial dimensions, which are width and height, of the feature maps, making the computation more efficient and the network more resilient to spatial variations in the input. Max pooling selects the maximum value in each patch of the feature map, effectively reducing the size while preserving important features. Example is a 2 by 2 max pooling layer applied to a feature map would downsample it by selecting the maximum value in each 2 by 2 region. Average pooling computes the average of each patch of the feature map, resulting in a smoother and smaller output. Convolutional neural networks architectures. Some of the common ones are LeNet, AlexNet, VGG, and ResNet. Let's go over LeNet. One of the earliest CNN architectures, LeNet, was developed for digit recognition. It consists of two convolutional layers followed by pooling layers and then fully connected layers for classification. Use case: LeNet is commonly used for recognizing handwritten digits in the MNIST dataset. AlexNet. AlexNet popularized CNNs by winning the ImageNet competition in 2012. It introduced deeper architecture with more convolutional layers and the use of ReLU activation functions, dropout for regularization, and GPU for training. Use cases: AlexNet is used for large scale image classification tasks. VGG. VGGNet introduced a very deep architecture with small 3 by 3 filters, demonstrating that depth, that is, more layers, significantly improves model performance. Use case: VGG is widely used in image classification and feature extraction tasks. ResNet. ResNet introduced the concept of residual learning, where shortcut connections, identity mappings, skip one or more layers, allowing for much deeper networks without suffering from the vanishing gradient problem. Use cases: ResNet is used in various computer vision tasks, including image classification, object detection, and segmentation. Now let's look at recurrent neural networks, RNNs, and LSTMs. Recurrent neural networks, RNNs, are designed to handle sequential data, making them suitable for tasks like time series, forecasting, natural language processing, and speech recognition. Understanding sequential data. Unlike independent data points in traditional datasets, sequential data points and are dependent on previous ones. Examples include sentences in natural language processing, where the meaning of a word often depends on the preceding words. Challenge: RNNs are designed to maintain a memory of previous inputs, which is crucial for understanding context in sequences. LSTM architecture and operations. LSTM networks. Long short term memory LSTM networks are a type of RNN designed to overcome the limitations of standard RNNs, particularly the issue of long term dependencies. LSTMs use a set of gates: input, forget, and output gates to control the flow of information, allowing the network to retain relevant information over long sequences. Let's look at the different gates. Input gate decides what new information should be added to the cell state. Forget gate which decides what information should be removed from the cell state. And then there's output gate, which determines the output based on the cell state and input. Example is in a language model, LSTMs can be used to predict the next word in a sentence, taking into account the entire preceding context. Applications in natural language processing and time series analysis. Natural language processing (NLP). LSTMs are widely used in tasks such as machine translation, text generation, sentiment analysis, and speech recognition. Example is in sentiment analysis, an LSTM can analyze the sentiment of a sentence by considering the entire sequence of words. Time series analysis. LSTMs are also effective in forecasting tasks such as predicting stock prices or weather conditions, where the future values depend on the past trends. Example, an LSTM can be trained to predict the next day's stock price based on previous prices. Transformer networks have revolutionized natural language processing by introducing a mechanism that allows the model to focus on specific parts of the input sequence, regardless of their position. Self-attention mechanism. The self-attention mechanism enables the model to weigh the importance of different words in a sentence when encoding a particular word. This allows the model to capture long-range dependencies more effectively than RNNs or LSTMs. Example is in a translation model, the word blank in he went to the blank would have different meaning depending on the surrounding words, and self-attention allows the model to consider these words appropriately. Scaled dot product attention. A common implementation of self-attention where the attention scores are computed as the dot product of query and key vectors, scaled by the square root of the dimension. Transformer architecture. The transformer architecture consists of an encoder and a decoder, both of which are built from self-attention and feed-forward layers. The encoder processes the input sequence while the decoder generates the output sequence one element at a time. Multi-head attention. The transformer uses multiple self-attention heads to capture different types of relationships in the data. Positional encoding. Since transformers do not have a built-in mechanism to handle the order of elements in a sequence, positional encodings are added to input embeddings to inject sequence information. Example is the transformer architecture is the foundation of models like BERT, which is the bidirectional encoder representations from transformers, and GPT, which is generative pre-trained transformer, which are used for tasks ranging from text classification to text generation. Applications in natural language processing. Language modeling. Transformers are widely used in language modeling tasks where they generate coherent and contextually relevant text. Example is GPT-3, a transformer-based model can generate human-like text given a prompt, making it useful in content creation and chatbots. Machine translation. Transformers have set new benchmarks in machine translation tasks by efficiently capturing the context of the source language to generate accurate translations in the target language. Example is the transformer-based model in Google Translate helps produce high-quality translations by understanding the nuances of different languages. Transfer learning and fine-tuning. Training deep learning models from scratch often requires vast amount of data and computational resources, which may not always be feasible. Transfer learning offers a solution by allowing you to leverage pre-trained models which have already learned useful features from large datasets. By transferring this knowledge to a new task, you can significantly reduce the time and data required to train a model. In this particular section, we will explore the concept of transfer learning, how to use pre-trained models from libraries like Torch Vision and Hugging Face transformers, and the strategies for fine-tuning models to suit domain-specific tasks. We will also discuss the differences between feature extraction and fine-tuning strategies. Introduction to transfer learning. Transfer learning is a powerful technique in deep learning where a model developed for one task is reused as the starting point for another task. This approach is particularly used when you have limited data for the new task but can access a model pre-trained on a large dataset. Concept of transfer learning. Transfer learning involves taking a model trained on a large dataset, example ImageNet for image classification, and adapting it to a new related task by either using it as a fixed feature extractor or fine-tuning it on the new dataset. Example is using a ResNet model pre-trained on ImageNet to classify medical images by fine-tuning the last few layers on a medical dataset. What are the benefits of transfer learning? First one is reduced training time. Since the model has already learned useful features, the training process is faster compared to training from scratch. Then there's improved performance. Transfer learning can lead to better performance on the target task, especially when the target dataset is small. And then there's lower data requirements. It allows effective model training even with limited label data. Now let's see how using pre-trained models for Torch Vision and Hugging Face transformers. The pre-trained models are readily available through popular libraries like Torch Vision for computer vision tasks and Hugging Face transformers for natural language processing. These models serve as a starting point for transfer learning. First, pre-trained models in Torch Vision. Torch Vision offers a variety of pre-trained models for tasks like image classification, object detection, and segmentation. These models are trained on large datasets like ImageNet. Example is loading a pre-trained ResNet model, where I have importing torchvision.models as models, and then the variable ResNet equal to models.resnet50, and the argument is pre-trained equal to true. What are the applications? You can use these models directly for inference or adapt them to your specific task through fine-tuning. Pre-trained models in Hugging Face transformers. The Hugging Face transformers provides access to a wide range of pre-trained models for NLP tasks such as text classification, named entity recognition, and text generation. Example is loading a pre-trained BERT model for text classification. So I'm importing BERT model and BERT tokenizer from transformers here, and I'm created a variable model which takes in the BERT model, calls the from pre-trained function, and loads in the BERT base uncased. Then I'm creating a variable tokenizer, and using the BERT tokenizer I'm calling the from pre-trained function and pass it BERT base uncased. Applications of this include models that can be fine-tuned for tasks like sentiment analysis, question answering, and machine translation. Fine-tuning models for domain-specific tasks. Fine-tuning involves further training a pre-trained model on a specific task, allowing it to adapt to the nuances of the new dataset. Fine-tuning process. The fine-tuning typically involves freezing the early layers of the model, which capture general features, and training the later layers on the new task. Example is fine-tuning a ResNet model on a medical imaging dataset by freezing the convolutional layers and training the fully connected layers. Here, I am running a for loop for param in resnet.parameters, param.requiredGrad equal to false. Then I'm replacing the final layer with a new one for the specific task by calling resnet.fc equal to torch.nn.linear, and I'm passing it two arguments, resnet.fc.inFeatures and num classes. Hyperparameter tuning. During fine tuning, it's essential to carefully select hyperparameters such as learning rate and batch size to avoid overfitting, especially if the new dataset is small. Challenges in fine tuning. First one is overfitting. Fine tuning on a small dataset can lead to overfitting, where the model becomes too tailored to the training data and fails to generalize to new data. Catastrophic forgetting. In the fine tuning process is too aggressive, the model might forget the useful features it learned from the original dataset, leading to degraded performance. Feature extraction versus fine tuning strategies. When using transfer learning, there are two main strategies: feature extraction and fine tuning. The choice between these strategies depend on the size of your dataset and the similarity between the original and target tasks. Feature extraction. In feature extraction, the pre-trained model is used as a fixed feature extractor, meaning that the weights of the pre-trained model are frozen and only the final classification layer is trained on the new dataset. Example is using a pre-trained ResNet model to extract features from images, then feeding those features into a new classifier trained on your specific dataset. So here for param in ResNet.parameters, param.requiredGrad equal to false. When to use it? Feature extraction is ideal when you have a small dataset and the new task is similar to the original task the model was trained on. Fine tuning. Fine tuning involves unfreezing some or all of the layers of the pre-trained model and retraining them on the new dataset. This allows the model to adapt more specifically to the new task. Example is fine-tuning all layers of a BERT model on a domain-specific text classification task. Model.train. Set the model to training mode to fine-tune. When to use? Fine-tuning is preferred when the new task is somewhat different from the original task, or when you have a larger dataset that can support more extensive retraining. Handling complex data. In the realm of deep learning, dealing with complex data types such as images, text, and time series requires specialized techniques and careful preprocessing. Whether you are enhancing image datasets with augmentation, preparing text data for natural language processing, or engineering features for time series forecasting, understanding how to handle these data types is crucial. This section will cover advanced techniques for processing and preparing complex data for use in deep learning models. We will explore image data augmentation methods, text preprocessing, and tokenizing strategies, and the unique challenges of handling time series data. Image data augmentation techniques. Data augmentation is a powerful technique used to artificially increase the size and diversity of an image dataset by applying random transformations. This helps prevent overfitting and improve the generalization ability of deep learning models. Random cropping, flipping, and rotation. Random cropping technique involves randomly selecting a sub-region of an image and cropping it out. It helps the model become more robust to variations in object positioning within images. Example here from torchvision.transformers, I'm importing random crop and I'm creating a variable transform where I'm calling the random crop function with the size of 224 by 224. Flipping. Random horizontal or vertical flipping of images help the model learn that the object's orientation is irrelevant to the classifications. Example here is I'm importing random horizontal flip from torchvision.transformers, and to the variable transform I am calling the function random horizontal flip with p equal to 0.5. Rotation. Rotating images by random degree helps the model become invariant to rotations, which is important for tasks where object orientation varies. Example here, I am importing random rotation from torchvision.transformers, and to the transform variable I'm calling the function random rotation degrees equal to 45. Color jittering, brightness contrast adjustment. Color jittering, this technique randomly changes the brightness, contrast, saturation and hue of an image, simulating different lighting conditions and making the model more robust to such variations. Example, from torchvision.transformers I'm importing color jitter, and we call this function color jitter and assign it to transform variable by passing brightness of 0 0.5, contrast 0 0.5, saturation 0 0.5 and hue of 0.1. Brightness and contrast adjustment. Similar to color jittering, this method focuses specifically on altering the brightness and contrast of images. Example, here I am importing adjust brightness and adjust contrast from torchvision transformers and calling this function with a brightness factor of 0.3. Text data pre-processing and tokenization. Text data requires specific pre-processing steps to convert raw text into a format that can be fed into deep learning models. Tokenization in particular is a key step in transforming text into tokens that represent the smallest units of meaning. Tokenization methods, word level and character level. Let's look at word level tokenization. This method splits text into words, treating each word as a separate token. It's the most common form of tokenization and is often used in tasks like text classification and sentiment analysis. Here is an example where I'm importing the word tokenize from nltk.tokenize, and to the variable tokens I'm calling the word tokenize function and passing it. This is an example sentence. Character level tokenization. This approach breaks text down into individual characters, making it useful for tasks like text generation or language modeling where finer granularity is required. Example is creating a tokens variable and calling the list and passing it. This is an example sentence. Handling sequence of variable lengths. First, by padding. Since neural networks requires inputs of the same length, shorter sequences are often padded with a special token, example zeros, to match the length of the longest sequence in the batch. Here in this example, I am importing pad sequences from keras.preprocessing.sequence and calling the pad sequences with sequences max length is 100 and padding equal to post and assigning it to padded sequence variable. Truncation. If sequences are too long, they might be truncated to a maximum length to reduce computational load and prevent memory issues. Here is an example where I am calling the pad sequences with sequences max length 100 and truncating to post and assigning it to truncated sequences. Handling long sequences. For very long sequences, advanced techniques like attention mechanisms, as in transformers, can be used to focus on the most relevant parts of the sequence, reducing the need for padding or truncation. Time series data handling. Time series data presents unique challenges because of its sequential nature and temporal dependencies. Handling this type of data effectively is key for tasks like forecasting, anomaly detection, and temporal pattern recognition. Temporal convolutions and recurrent architecture. Temporal convolutions. Convolutional layers can be adapted to process time series data by applying filters over temporal windows capturing patterns over time. Example is temporal convolutional networks (TCNs) apply causal convolutions to ensure that the model doesn't violate the sequence order by incorporating future information. Recurrent architectures. Recurrent neural networks or RNNs and LSTM, which is long short term memory networks, are specifically designed for sequential data, maintaining a memory of past inputs through hidden states. Here is an example where I'm importing importing torch.nn as nn, and with the variable rnn I'm assigning nn.lstm where I'm passing input size of 10, hidden size 50, and number of layers equal to 2. Feature engineering for time series forecasting. Lag features. Lag features are created by shifting the time series data by one or more time steps, allowing the model to capture temporal dependencies. Example is creating a lagged version of a time series to predict the next value based on the previous values. Rolling statistics. Calculating rolling means, variances, and other statistics over a moving window helps in capturing trends and patterns over time. Example is data of rolling mean equal to data of value dot rolling window is 5 dot mean function. Seasonality and trends. Identifying the modeling seasonal patterns, example daily, weekly, monthly, and trends in the data is crucial for accurate forecasting. Example is decomposing a time series into its trend, seasonality, and residual components. Model deployment and production. Once a deep learning model is trained and evaluated, the next critical step is deploying it into production. Deployment involves not only saving and loading models but also ensuring they can efficiently serve predictions in real world applications. This section will guide you through the process of saving and loading models in PyTorch, serializing modules for deployment using Torch script and ONNX, serving models through popular frameworks like Flask, FastAPI, and AWS Lambda, and implementing strategies for model monitoring and versioning in production. By mastering these techniques, you'll be equipped to take your models from development to real world deployment with confidence. Saving and loading models with torch.save and torch.load. Saving and loading models are fundamental operations that allow you to preserve the state of a trained model and reuse it later for inference or further training. Saving models. State dictionary. In PyTorch, the recommended way to save a model is by saving its state dictionary, which contains the model's parameters, weights, and biases. Example is import torch and torch.save model.stateDict, model.pth. Entire model. While saving the entire model is possible, it is less flexible and not recommended for most use cases, especially when dealing with dynamic computational graphs. Here is an example: torch.save model and model path. Loading models. Loading state dictionary. To load a model, you need to first initialize the model architecture and then load the saved state dictionary into it. Here is an example. So model equal to the model class, pass the arguments and the KW arguments, model dot load state dictionary, where I'm saying torch dot load model dot pth, and then model dot evaluate. I set the model to evaluation mode. Loading entire model. If you save the entire model, you can load it directly, though this method is less flexible. Here is an example: model equal to torch.load model.pth. Model serialization and deployment with Torch script and ONNX. For deploying models in production, you need to serialize them in a format that can be efficiently executed in various environments. Torch script. TorchScript is an intermediate representation of PyTorch model that can be optimized and executed in a production environment without requiring a Python runtime. Scripting. Convert a PyTorch model to TorchScript using scripting, which automatically converts the model. Scripted model equal to torch.jet.script and pass the model, and torch.jet.save say scripted model and model scripted.pd. Tracing. Alternatively, you can trace a model that has a fixed input size to torch script. Here is an example. Traced model equal to torch.jet.trace and pass the model and example input, torch.jet.save, pass the traced model and model trace.pd. Deployment. Torch script models can be deployed to environments like mobile devices, edge devices, or cloud servers where a full Python runtime might not be available. ONNX, or Open Neural Network Exchange. ONNX is an open standard for representing machine learning models, allowing models trained in PyTorch to be deployed in a variety of platforms and runtimes such as TensorRT or ONNX runtime. Exporting to ONNX. Convert a PyTorch model to the ONNX format. torch.onnx.export pass the model, example input, and the name model.onnx. Deployment. ONNX models can be deployed in environments that support ONNX, making it easier to integrate with other frameworks and tools beyond PyTorch. Serving PyTorch models with Flask, FastAPI, and AWS Lambda. Serving a model involves setting up an API that can receive data, pass it to the model for prediction, and return the result. Various frameworks can help with this process. First, serving with Flask. Flask is a lightweight web framework that can be used to create a simple API for serving PyTorch models. Here is an example. So from Flask, I'm importing Flask request and JSONify, and then I'm importing Torch. App equal to Flask, give the name, model equal to the model class, and pass the arguments and kwargs. Model.load state dict and pass torch.load model.pth, and then start the evaluation by saying model.eval. Then @app.route, setting the route here, /predict. So every time anyone hits the URL predict, it needs the methods which is post, and predict function will have a variable data request.getJSON force true, input tensor equal to torch.tensor, and pass the parameter data input, output equal to model input tensor, and return JSONify output to list. So the output will be converted into JSON and returned back. If name equal to underscore underscore main, app.run debug equal to true. This is just a required thing in Flask. Serving with FastAPI. FastAPI is a modern fast web framework that is well suited for building APIs with automatic documentation and validation. So here from FastAPI, I'm importing FastAPI, importing Torch, app equal to FastAPI function, model equal to the model class, pass the arguments and kwargs, model.load state dict and torch.load, load the model, and if start evaluation by model.eval. And again here the path app.post predict, async function predict with pass input data as list of float, input tensor equal to torch.sensor input data, output equal to model input sensor, and then return this output to list to whoever called it. If name equal to main, import uvcon and uvcon.run app host, whichever host URL you're running it on, and port equal to 8000, set the port based on what your port is. Serving with AWS Lambda. AWS Lambda is a serverless computing service that lets you run code without provisioning servers. You can deploy a PyTorch model using Lambda to create a scalable and cost-effective model serving endpoint. Steps are: package your model and code, deploy to AWS Lambda using a tool like AWS SAM or the serverless framework, and integrate with API gateway to create an HTTP endpoint for serving predictions. Model monitoring and versioning in production. Once deployed, models in production must be monitored for performance and managed through versioning to ensure reliability and continuous improvement. Model monitoring. Importance. Monitoring is crucial for detecting issues like model drift, where the model's performance degrades over time due to changes in data patterns. Metrics. Track metrics such as prediction accuracy, latency, error rates, and resource utilization. Tools. Use monitoring tools like Prometheus, Grafana, or specialized AI monitoring platforms like Seldon or Neptune.ai to keep track of these metrics. Model versioning. Versioning allows you to manage multiple versions of a model, enabling rollback to a previous versions if needed. and A/B testing of different models. Techniques: use model registries and versioning tools like MLflow, DVC, which is Data Version Control, or AWS SageMaker Model Registry. Deployment strategy: implement canary deployments or blue-green deployments to safely transition between model versions in production. Debugging and troubleshooting: even with well-structured code, issues can arise during the development of deep learning models. Debugging and troubleshooting are essential skills for identifying and resolving errors, improving model stability, and optimizing performance. In this section, we will explore common errors and warnings in PyTorch, effective debugging techniques, strategies for handling numerical stability, issues like NANs and infinites, and tools for profiling and optimizing PyTorch code. By mastering these skills, you can ensure your models run smoothly and efficiently in both development and production environments. Understanding common PyTorch errors and warnings. PyTorch users often encounter various errors and warnings, especially when experimenting with complex models or data pipelines. Understanding these messages is crucial for quickly diagnosing and fixing issues. Common errors. First one, shape mismatch error. These errors occur when operations are performed on tensors with incompatible shapes. Common examples include trying to add tensors of different dimensions or incorrectly defining model layers. Here is an example of how the error looks like. Runtime error: the size of tensor a 10 must match the size of a tensor B 12 at non-singleton dimension 0. Solution: check the shapes of the tensors involved using tensor.shape and ensure they are compatible for the intended operation. Type errors. PyTorch operations are sensitive to tensor data types. A common mistake is performing operations between tensors of different types, such as float32 and int64. This is an example of the error. Runtime error: expected object of scalar type float but got scalar type long for argument number 2 weight. Solution: ensure tensors are of the same type using tensor.type and convert them if necessary using tensor.float or tensor.long. CUDA errors. These errors are related to GPU usage and occur when operations are performed on tensors that are not on the same device or when there is insufficient GPU memory. Example is runtime error: CUDA out of memory. Tried to allocate 1 GB GPU 0 11 is to 11.17 GB, total capacity 8.51 GB already allocated. Solution: free up memory by deleting unnecessary variables with del, use smaller batch sizes, or move some tensors to the CPU using tensor.cpu. Common warnings. User warnings. PyTorch often issues warnings when it detects potentially problematic operations, such as using deprecated features or inefficient methods. Example: user warning: using a target size torch.size 10,1 that is different to the input size torch.size 10 is deprecated. Solution: pay attention to warnings and update your code to comply with the latest recommended practices. Deprecation warnings. These warnings inform you that a particular feature or function will be removed in a future version of PyTorch. Solution: replace the deprecated features with the modern equivalents as suggested in the warning message. Debugging techniques. Printing tensors using PyTorch debugger, which is PDB. Effective debugging techniques are essential for identifying and resolving issues in your code. Printing tensors. One of the simplest yet most effective debugging technique is printing the values and shapes of tensors at various points in your code. This helps verify that operations are producing the expected results. Here is an example: print f tensor shape tensor.shape. Print at tensor values tensor. Inspecting gradients. You can also print the gradients of the tensors after the backward pass to ensure they are being computed correctly. There is an example of how to print that. Print gradients tensor.grad. Using PyTorch debugger, which is PDB. PyTorch can be debugged using Python's built-in PDB debugger, which allows you to set breakpoints, step through code, and inspect variables. Setting a breakpoint. Import PDB set trace at the point where you want to start debugging. The execution will pause, allowing you to inspect the environment. Here, if you see import PDB, and I have function forward pass which has the variable x, and pdb.setTrace over there where debugging begins, and y equal to x plus 2 return y. It will tell you what happened. Common commands are n, which is next, execute the next line of code while debugging. C, continue execution until the next breakpoint. Q is quit, exit the debugger, and P, variable name, prints the value of the variable. Handling numerical stability issues, NaN, which are not in numbers, and infinites. Numerical stability is a common concern in deep learning where certain operations can lead to NaN, or not a number, or infinite values, causing the model to fail. Common causes of NaNs and infinites. Exploding gradients. Gradients that grow exponentially during backpropagation can lead to NaNs or infinities in the model's parameters. Solution: use gradient clipping to limit the size of the gradients. torch.nn.utils.clip grad norm function with model parameters and max norm equal to 1.0. Division by zero. Certain operations like division or logarithmics can produce NaNs or infinite when the input is 0 or negative. Solution: add a small epsilon value to the denominator to prevent division by 0. Here, result equal to x divided by y plus 1 e raised to minus 8. Overflow in exponentials. Exponential functions can quickly grow to very large values leading to overflow. Solution is use the torch.clamp function to limit the range of inputs. So torch.clamp x minimum equal to minus 10, maximum equal to 10. Detecting and handling NaNs and infinities. NaN detection, use the torch.isNaN function to detect NaNs in tensors. Example, if torch.isNaN a particular tensor .any, then print NaN detected. Infinity detection. Similarly, torch.isInf can be used to detect infinite values. Example, if torch.isTensor.any, print infinity detected. Debugging NaNs. If NaNs or infinities are detected, backtrack through your operations to find where they first appear and modify the operation to ensure numerical stability. Profiling and optimizing PyTorch code. Profiling and optimizing your PyTorch code is crucial for improving performance, especially when training large models on substantial datasets. Profiling with torch.profiler. PyTorch torch.profiler module provides tools for profiling model performance, identifying bottlenecks, and understanding how different parts of your code execute. Here is an example. Import torch from torch.profiler, import profile, record function, and profiler activity. With profile, activity is equal to profiler activity.cpu, profiler activity.cuda, and record shapes equal to true as prof with record function, model inference, model input sensor. Print prof.keyaverages function table sort by CPU time total. Insight: profiling can reveal which operations are taking the most time, whether your model is effectively utilizing the GPU, and where you might have inefficiencies in your code. Code optimization techniques. Batching. Process data in batches rather than individually to take full advantage of GPU parallelism. Example is, instead of processing one image at a time, Use a batch of 32 images to maximize GPU utilization. Mixed precision training. Use mixed precision training to reduce memory usage and increase computational speed by using 16-bit floating point numbers where possible. Example here is model equal to model.half, input sensor is equal to input sensor.half. Avoiding Python loops. Replace Python loops with PyTorch operations whenever possible to leverage the power of vectorization and GPU acceleration. Example is instead of looping through tensors to add them, use tensor.sum dim equal to 0 for efficient computation. Distributed training and performance optimization. As deep learning models grow in complexity and size, the need for efficient training methods become increasingly important. Distributed training allows you to scale your training across multiple GPUs or even multiple nodes, significantly reducing training time. Additionally, techniques like gradient accumulation, mixed precision training, and various performance optimizations can help you make the most of your hardware resources. This section will guide you through the essentials of distributed training using PyTorch's distributed data parallel as well as strategies for optimizing model performance during training. By the end of this section, you will be equipped with the tools and knowledge to train large models efficiently and effectively. Distributed training with torch.nn.parallel.distributed data parallel. Distributed training enables you to leverage multiple GPUs or nodes to train your models faster. PyTorch's torch.nn.parallel.distributed data parallel or DDP is the recommended way to distribute your training across multiple devices. Introduction to distributed data parallel. DDP synchronizes gradients and updates model parameters across multiple processes running on different GPUs or nodes. This ensures that each GPU contributes to the training process, effectively parallelizing the workload. Example is in a multiple GPU setup, each GPU processes a subset of the training data, and DDP ensures that all GPUs stay in sync by averaging gradients during backpropagation. Setting up DDP. Here is step 1. Initialize the process group for communication between GPUs. Example, import torch.distributed as dist, then dist.init process group, pass backend equal to nccl, init method equal to environment. Step 2. Wrap your model with distributed data parallel. Model equal to torch.nn.parallel.distributed data parallel, pass it model, and device IDs equal to local rank. Setup step 3. Ensure that each process is assigned a specific GPU using the local rank argument. Example, torch.cuda set device local rank, model.cuda local rank. Best practices for DDP. Data loader with distributed sampler. Use torch.utils.data.distributed sampler to ensure that each GPU receives a different subset of data, preventing overlap and ensuring efficient use of the dataset. Example is train sampler equal to torch.util.data.distributed sampler and pass the train dataset. Train loader equal to torch.util.data loader. Dataset is equal to train dataset and sampler is equal to train sampler. Gradient synchronization. DDP automatically synchronizes gradients across all processes, so you don't need to manually handle gradient averaging. Handling multiple nodes. For multiple node setups, ensure that the init method is init process group in the init process group is set up correctly to allow nodes to communicate with each other. Gradient accumulation and gradient clipping. Training large models on limited GPU memory can be challenging. Gradient accumulation and gradient clipping are techniques that help manage memory and ensure stable training. Gradient accumulation. Gradient accumulation involves accumulating gradients over multiple forward passes before performing a backward pass and optimizer step. This allows you to effectively simulate a larger batch size than what your GPU memory can handle. Here is an example where I'm saying optimizer.zeroGrad for I in range accumulation steps, output equal to model of input, loss equal to criterion of output comma target, loss.backward where you accumulate gradients, optimizer.step, update weights after accumulation. When to use it? Use gradient accumulation when your desired batch size exceeds the average GPU memory, allowing you to train with larger effective batch sizes. Gradient clipping. Gradient clipping involves capping the gradients to a maximum value to prevent them from becoming too large, which can cause unstable training or gradient explosions. torch.nn.utils.clip grad norm when pass model.parameters max norm equal to 1.2 is a good example. When to use it? Gradient clipping is particularly useful in training deep neural networks or recurrent models when gradients can grow exponentially during backpropagation. Mixed precision training with NVIDIA Apex. Mixed precision training leverages the capabilities of modern GPUs by using both 16-bit and 32-bit floating point operations, leading to faster computation and reduced memory usage. Introduction to mixed precision. Now, mixed precision training allows you to train models faster by using 16-bit floats FP16 where possible, while still maintaining the precision of 32-bit floats FP32 for critical operations. This is especially beneficial on an NVIDIA GPUs that support tensor cores, which are optimized for FP16 operations. Setting up mixed precision training using NVIDIA Apex. NVIDIA's Apex library provides tools for easy implementation of mixed precision training in PyTorch. Here is an example from Apex import AMP. Model comma optimizer, you can call the function initialize from AMP by calling amp.initialize and pass the model, optimizer and opt level equal to 0.1. Automatic loss scaling. Apex automatically scales the loss to prevent underflow when using FP16, ensuring stable training. Best practices. Choosing optimization levels. Apex offers different optimization levels O0, O1, O2 and O3 that balance between speed and precision. Start with O1 as it offers a good trade-off between performance and stability. Monitoring for NANs. Mixed precision training can sometimes lead to numerical instability. Monitor your trainings for NANs and infinities and use gradient clipping if necessary. Performance optimization techniques. You have parallelism, you have asynchronous processing. Optimizing performance in PyTorch involves making the most of your hardware resources through parallelism and asynchronous processing. Parallelism, data parallelism, distributes the data across multiple GPUs, allowing each GPU to process a portion of the data in parallel. Here is an example where I have a variable model with torch.nn.dataParallel, pass the model to it, and output equal to model and pass input as the parameter. Model parallelism splits the model itself across multiple GPUs, useful for very large models that don't fit into a single GPU's memory. Example is part 1.2 CUDA of 0, part 2.2 CUDA of 1. Asynchronous processing. Now, asynchronous data loading using multiple workers in data loader allows for asynchronous data loading, reducing the time your GPU spends idle. Here is an example: train loader equal to torch.utils.data data loader function and pass a dataset, batch size equal to 32 and number of workers equal to 4. Asynchronous CUDA operations. PyTorch operations on CUDA tensors are asynchronous by default, allowing the GPU to perform computations while the CPU prepares the next batch of data. Profiling and optimization. Profiler. Use PyTorch Profiler to identify bottlenecks in your code and optimize accordingly. Here is an example. You can say with torch.profiler.profile activities torch.profiler.profileractivity.cpu and torch profiler activity.q.sp, and call the model with input and print p.keyaverages.table sort by self CUDA time total. Memory management. Monitor GPU memory usage with torch.CUDA memory summary function and optimize by clearing cache or using torch.nograd function in inference mode to reduce memory consumption. Custom layers and loss functions. While PyTorch provides a wide range of built-in layers, loss functions, and activation functions, there are times when you need to customize these components to fit specific needs or experiment with novel architectures. This section covers how to create custom neural network layers and loss functions using torch.nn.module, implement advanced activation functions, and apply regularization techniques to prevent overfitting. By mastering these concepts, you'll gain great flexibility in designing and optimizing deep learning models tailored to your specific task. Creating custom neural network layers with torch.nn.module. Now, the custom layers allow you to implement unique operations that are not available in PyTorch's standard library, providing more control over the model architecture. So, subclassing torch.nn.module. To create a custom layer, subclass torch.nn.module and implement the init method to define the layer's parameters and the forward method to define the computation. Here is an example where I'm importing torch nn, and then I create a class custom layer nn.module as a parameter. Now calling the define function and pass itself in features and out features. Call the super function, pass it the custom layer and self, and call the initialization method. Then self.linear equal to nn.linear in features and out features, and self.relu equal to nn.relu. And then the forward function where self and x is passed, and x equal to self.linear of x and x equal to self.relu of x, and return the value of x. Usage. Once defined, the custom layer can be used like any other PyTorch layer in neural network. Here is an example. Model equal to nn.sequential and pass custom layer 10,20 and nn.linear 20,10. Parameter initialization. Custom initialization. You can customize the initialization of layer parameters using methods such as torch.nn.init. Here is an example where I'm calling the init function self in features and out features, call the super method, pass the custom layer and self and init function, and then self.linear equal to nn.linear, pass the in features and out features, and then torch.nn.init Xavier uniform, and then pass self.linear.weight. Implementing custom loss function and metrics. Custom loss functions and metrics are essential when built-in options do not fit your specific problem or when you want to introduce novel evaluation criteria. First, creating custom loss functions. To create a custom loss function, define a new function or subclass torch.nn.module and implement the forward method to calculate the loss. Here is an example where I'm importing torch.nn.functional as f. Create the custom class with nn.module and define the two functions init and forward. Inside init, I'm just saying going to call the super class, pass the custom loss and self, and call the initialization method of super. And then in the forward function, I'm passing the self, output, and target, and loss equal to f dot MSE loss, pass output and target, plus 0.1 times torch of mean output, and then return the loss. The custom loss function can be used like any other loss function in your training loop. Here is an example. We create a criterion where custom loss and then loss equal to criterion, output, and target. Implementing custom metrics. Metrics evaluate the performance of your model on validation or test data. You can create custom metrics by defining a function that compares predictions with the ground truth. Here is an example where you have a custom accuracy function with predictions and targets. correct equal to a variable correct equal to predictions dot argmax dim equal to 1 equal to targets dot float. Then return correct dot sum divide by length of targets. Usage. Use custom metrics during model evaluation to gain insights beyond standard metrics like accuracy or loss. Here is an example where I have the accuracy variable. Call the custom accuracy function with predictions and targets and print accuracy 0.4f. Advanced activation functions, which are swish, mesh, and galue. Activation functions play a crucial role in introducing non-linearity into neural networks. While ReLU is the most common, advanced activation functions like swish, mesh, and galue can offer performance improvements in certain models. Let's look at swish. Swish is an activation function defined as f of x equal to x times sigmoid of x. It has been shown to perform better than ReLU in some deep networks. Here is a class swish nn.module where I am defining forward function, pass the self and x, and here return x times torch.sigmoid of x. Usage. Replace ReLU with swish in your model architecture when appropriate. Here is an example. Model equal to nn.sequential, nn.linear 10, 50, and swish and nn.linear 50, 10. Mesh. Now mesh is defined as f of x equal to x times tan h of soft plus x, where soft plus x equal to log of 1 plus exponential value of x. Mesh has been found to improve the performance of various architectures, especially in computer vision tasks. Here is an example of a class mesh nn.module, and the forward function with self and x returns x time torch of tan h f dot soft plus of x. User mesh can be used in place of ReLU or other activation functions in your model by saying model equal to nn.sequential, and then you have nn.con 2d where 364 kernel size equal to 3, stride equal to 1, padding is 1, and then call the mesh function, and then nn.maxpool 2d kernel size of 2 and stride of 2. Galue or Gaussian error linear unit. Galue is defined as f of x equal to x times 0.5 times 1 plus erf of x divided by square root of 2, where erf is the error function. It is used in models like BERT and has shown improved convergence properties in NLP tasks. So here is how you can create it. Class galue nn.module and the forward self.x return f.galue of x. Galue is often used in transformer models and can be substituted for other activations in models requiring smooth and non-linear behavior. So here a model nn.sequential where nn linear and has some parameters called the pass the Galue function, and linear and has some other values which are reverse 3072 768. Regularization techniques. There's dropout and then there's weight decay. Regularization is crucial for preventing overfitting, especially in complex models with a large number of parameters. Dropout. Now, dropout is a regularization technique that randomly sets a fraction of the input units to 0 during training, preventing the model from becoming too dependent on any particular node. Here is an example. Dropout layer nn.module. I have my init and function forward methods. Inside init, I am passing self and p equal to 0.5. Call the super, pass the class object dropout layer and self and initialize it, and self.dropout equal to nn.dropout p. For in the forward functions, pass self x and return self.dropout of x. Usage. Dropout is typically applied to fully connected layers in neural networks. Here is an example where we have the model equal to nn sequential, nn linear 512 256, nn.ReLU, and then nn.dropout of 0.5, and finally again nn.linear 256 by 10. Weight decay. Weight decay or L2 regularization penalizes large weights by adding a term to the loss function that is proportional to the sum of the squares of weights. Here is an example. Optimizer equal to torch.optim.sgd. Model parameters LR equal to 0.01 and weight decay here is 0.001. Weight decay is applied during optimization and helps prevent overfitting by discouraging overly complex models. Example of applying weight decay in optimizer using Python here. Optimizer is equal to torch.optim adam model.parameters LR equal to 0.001 and weight decay equal to 0.01. Research oriented techniques. In the rapidly evolving field of machine learning, conducting robust and reproducible research is crucial for ensuring that your findings can be validated and built upon by others. This section delves into the essential techniques that support research oriented workflows, including ensuring reproducibility on experiments, tracking experiments with specialized tools, optimizing hyperparameters, and staying current with the latest research. By mastering these techniques, you'll be better equipped to conduct high quality research that contributes meaningfully to the machine learning community. Reproducibility in machine learning experiments. Reproducibility is a cornerstone of scientific research, and in machine learning, it involves ensuring that your experiments can be reliably repeated with the same results. Importance of reproducibility. Reproducibility allows other researchers to verify your results, compare approaches, and build on your work. Inconsistent results can undermine the credibility of your findings and hinder progress in the field. Challenges. Machine learning experiments can be difficult to reproduce due to factors like random initializations, non-deterministic hardware operations, example GPU computations, and inconsistent data preprocessing. Techniques for ensuring reproducibility. Set random seeds. By setting random seeds for libraries like NumPy, PyTorch, and Random, you can control the randomness in your experiments. Here is an example. Import torch, import NumPy as np, and import random. I have function set seed which pass the seed in there. Torch.manual seed, you pass the seed, np.normal seed, pass the seed, and random.seed and seed variable as parameter. If torch.cuda is available, torch.cuda.manual seed, say pass seed, torch.cuda.manual seed all, pass the seed, torch.backends.queuednn dot deterministic equal to true, and torch.backends.queuednn.benchmark is equal to false, and set the seed here by 42 and test it out. Documenting dependencies. Use tools like pip, freeze, or conda and export to document the exact versions of libraries used in your environment. Here is an example: pip freeze to requirements.txt. Control hardware variations. When possible, run experiments on the same hardware or at least document the hardware used, as different GPUs or CPUs can lead to slightly different results due to hardware specific optimizations. Experiment tracking with tools like Neptune, weights, and biases. Experiment tracking is crucial for organizing, comparing, and sharing the results of different runs, especially when working on complex projects with multiple variables. Introduction to experiment tracking. Experiment tracking tools help manage and log the details of your experiments, such as hyperparameters, training metrics, model versions, and code changes. This ensures that you can trace back the steps that led to specific results. Benefits. These tools facilitate collaboration, reproducibility, and easier debugging by providing a clear history of your experiments. Neptune.ai. Neptune is an experiment tracking uh, and model registry tool that allows you to log and compare experiments in real time, making it easier to manage your research projects. Here is an example where I'm importing neptune.new as Neptune, and then run neptune.init with the project equal to whatever your workspace is and your project. Run with parameters equal to learning rate equal to 0.001, batch size of 32, then run matrix of train loss dot log of 0.5. Run dot stop. Features. Neptune offers features like dashboard visualization, automated logging, and integration with various machine learning frameworks. Weights and biases, or WNB. WNB is another popular experiment tracking tool that provides real-time visualization of your model training, hyperparameter tuning, and version control. Here's an example. Import WNB. WNB.init project equal to pass your project name. WNB.config update learning rate equal to 0.001 and epochs of 50. WNB log train loss of loss and WNB finish. WNB integrates with PyTorch and other frameworks, offering rich visualization, collaborative reporting, and easy sharing of experiment results. Hyperparameter tuning strategies, which are grid search, random search, and Bayesian optimization. Hyperparameter tuning is critical for optimizing the performance of machine learning models. Different strategies offer various trade-offs between exploration and efficiency. Grid search. Grid search systematically explores a predefined set of hyperparameters by evaluating all possible combinations. While exhaustive, it can be computationally expensive. Here is an example. From sklearn.model selection, import grid search CV. Param grid, learning rate of 0.01 and 0.001, batch size 32 to 64. Grid search CV, estimator equal to pass the model, and param grid is pass that param grid that we created, CV equal to 3. Now grid search.fit, xtrain, and ytrain. When to use? Grid search is ideal when you have a small number of hyperparameters and values to explore. Next one, random search. Random search selects hyperparameters randomly from a specified range, as the name suggests, offering a more efficient alternative to grid search by not evaluating every possible combination. Here is an example. From sklearn.model selection, import randomized search CV. Param dist equal to learning rate of 0.01 to 0.001, batch size 3264. Random search equal to random search CV, estimator equal to model, param distribution is the param dist that we created above, and n iteration equal to 10 and CV equal to 3. Random search.fit and pass xtrain and ytrain to it. When to use? Random search is more efficient than grid search when you have many hyperparameters on a large search space. Bayesian optimization. Now, Bayesian optimization is more sophisticated method than models that models the performance of hyperparameters with a probabilistic model and chooses the next set of parameters to evaluate based on expected improvement. Here is an example from Scopt. Import Bayes search CV. Now, Bayesian search equal to Bayesian search CV. Estimator model equal to model. Search spaces equal to param dist. And iterate equal to 10, CV equal to 3. Again, Bayesian search object variable dot fit xtrain and ytrain. When to use? Bayesian operations is highly efficient for complex models with many hyperparameters, as it intelligently explores the search space to find optimal values faster. Staying updated with research papers and conferences. The field of machine learning is fast-paced, with new research being published daily. Staying updated with the latest advancements is crucial for researchers and practitioners alike. Following research papers: ARXIV and Google Scholar. These platforms are essential for discovering and following the latest research papers. Setting up alerts for specific topics can help you stay informed. ARXIV, a repository of preprints where researchers publish their latest work before it's peer reviewed. Google Scholar provides citations, related papers, and the ability to create alerts for new papers in your field. RSS feed and email alerts. Use RSS feeds or email alerts to automatically receive updates
on new papers in your areas of interest. Example, set up a Google Scholar alert for deep learning or transformer networks. Participating in conferences. Top conferences. Major conferences like Neural IPS, ICML, and CVPR are where leading researchers present their latest work. Attending these conferences, whether in person or virtually, provides valuable insights and networking opportunities. Examples: Neuro IPS focuses on machine learning and computational neuroscience. ICML covers a broad range of topics in machine learning. CVPR specializes in computer vision and pattern recognition. Google them up and you'll know more. Workshops and tutorials. Conferences often feature workshops and tutorials on cutting edge topics, providing hands on learning opportunities and insights into emerging trends. Integration with other libraries. One of the strengths of PyTorch is its flexibility and ease of integration with other libraries in the machine learning ecosystem. Whether you are combining the strengths of PyTorch and TensorFlow, leveraging OpenCV for advanced computer vision tasks, or utilizing natural language processing libraries like SparseEY and NLTK, PyTorch's interoperability makes it a powerful tool for a wide range of applications. This section explores how to integrate PyTorch with other libraries, enhancing your ability to build complex multifunctional models and workflows. Interoperability between PyTorch and TensorFlow Keras models. While PyTorch and TensorFlow Keras are often seen as competing frameworks, there are situations where you might want to leverage models or components from both ecosystems. Understanding how to bridge the gap between them can be invaluable. Converting models between PyTorch and TensorFlow. Converting models between PyTorch and TensorFlow Keras allows you to reuse existing models, take advantage of specific features of each framework, and deploy models in environments that prefer one framework over the other. Using Onyx for, for conversion, Onyx or Open Neural Network Exchange is an open format that allows you to convert models between different frameworks including PyTorch and TensorFlow. Example, converting a PyTorch model to Onyx and then to TensorFlow. We'll see it in the next slide, the example. And using Keras to load and convert models. You can also load Keras models in PyTorch by manually converting weights and architectures or using libraries like Onyx to Keras. Let's look at the example. Now here's the example for converting a PyTorch model to Onyx and then to TensorFlow. You first import torch, you import torch.onyx, export PyTorch model to Onyx by doing torch.onyx.export, pass the model, input tensor and model.onyx file. Convert Onyx model to TensorFlow, first import Onyx, then from Onyx tf dot backend import prepare. Now Onyx model variable equal to Onyx dot load and pass the name model dot Onyx tf underscore rep prepare Onyx model, and finally again tf which is TensorFlow dot rep export graph model dot pv. Using PyTorch models in TensorFlow Keras. Embedding PyTorch within TensorFlow workflows. Sometimes it's beneficial to run a PyTorch model as part of the TensorFlow Keras pipeline. This can be achieved by exporting the PyTorch model to Onyx and then importing into TensorFlow. Example is use tf.keras model to load an Onyx model and integrate it into a larger TensorFlow model. Mixed environments. In complex workflows, PyTorch and TensorFlow models can be used together, each handling different parts of the pipeline. This is particularly useful in research environments where flexibility is the key. Using PyTorch with OpenCV for computer vision tasks. OpenCV is a widely used library for computer vision tasks, and combining it with PyTorch allows you to build powerful models that leverage both image processing and deep learning. Pre-processing images with OpenCV. OpenCV provides a rich set of tools for image manipulation which can be used to pre-process images before feeding them into PyTorch model. Here's an example of reading and processing images with OpenCV, where you import CV2, import the torch, import torch vision.transformers as transformers. Now read an image with OpenCV. I'm saying image equal to CV2 dot image read, which is imread, and give the image name image.jpg. Image equal to CV2 CVT color image comma CV2 dot color BGR to RGB. Now convert to PyTorch sensor. Transform equal to transforms dot to tensor function, then image tensor equal to transform the image. Common pre-processing techniques. Resizing. Use CV2.resize to resize images. Normalization. Normalize pixel values using OpenCV or PyTorch's transform.normalize. Real-time inference with OpenCV and PyTorch. OpenCV's real-time video processing capabilities can be combined with PyTorch's models to perform tasks like real-world, real-time object detection or face recognition. Example is on the next slide, but before that, edge computing, combining PyTorch and OpenCV on edge devices such as Raspberry Pi enables real-time inference for IoT applications. Let's look at an example. This is an example for real-time object detection with a PyTorch model. We have cap variable equal to cv2 dot video capture 0, while true ret comma frame equal to cap dot read. If not ret, then break. Pre-process the frame. Image tensor equal to transform frame. Perform inference with PyTorch model. Output equal to model image tensor dot unsqueeze 0. Now here we process and display the results. Assume output contains bounding boxes or class predictions. So CV2 I am show, which is image show frame by frame. If CV2 dot wait key 1 and 0x ff equal to ORD of q, then break. Finally cap dot release and CV2 dot destroy all windows. Integration with natural language processing libraries like SPA-CY and NLTK. Now, PyTorch's flexibility makes it easy to integrate with popular NLP libraries like SPA-CY and NLTK, enhancing your ability to build and deploy sophisticated NLP models. Using PyTorch with SPA-CY. SPA-CY is a powerful NLP library that offers pre-trained models for tasks like tokenization, named entity recognition, and dependency parsing. Combining SPA-CY with PyTorch allows you to pre-process text data efficiently and build custom NLP models. Example is tokenizing text with SPA-CY and using it in a PyTorch model. Here is the example. Import spacey and import torch. Now spacey is SPA-CY, depends on how you say it. NLP equal to spacey.load n core web sm. Doc equal to NLP. PyTorch is a deep learning framework. Tokens equal to token.next.text for token in doc. This converts tokens to PyTorch tensors, example using a word embedding model. Text preprocessing. Use spacey or SPA-CY for advanced text preprocessing tasks such as lemmatization and part of speech tagging before feeding the processed text into a PyTorch model. Using PyTorch with NLTK. NLTK, which is also Natural Language Toolkit, is a comprehensive library for building Python programs to work with human language data. It provides tools for text processing, tokenization, and more. Here is an example of tokenizing and processing text with NLTK. Import NLTK first, and from NLTK.tokenize import word tokenize, and then import torch. NLTK.download punct text equal to PyTorch and NLTK work well together. Tokens equal to word tokenizes using the text above. Convert tokens to indicate or embeddings for use in PyTorch model here. Integrating with PyTorch models. NLTK can be used to pre-process text data, generate features, and then feed these features into PyTorch model for training or inference, contributing to PyTorch and community engagement. PyTorch is an open source deep learning framework that thrives on the contributions of its vibrant community. Contributing to PyTorch not only helps the ecosystem grow but also enables developers to engage with cutting edge technologies and collaborate with experts worldwide. This section covers the steps involved in contributing to PyTorch, including understanding its contribution guidelines, contributing bug fixes or new features, and engaging with the PyTorch community through forums, mailing lists, and social media. By participating in the development of PyTorch, you can have a meaningful impact on the future of the framework while building your skills and professional network. Understanding PyTorch's contribution guidelines and codebase. Before contributing to PyTorch, it's essential to familiarize yourself with the contribution guidelines and the structure of the PyTorch codebase. The PyTorch contribution guidelines. PyTorch maintains a set of contribution guidelines that outlines the process for submitting changes, whether they are bug fixes, documentation improvements, or new features. Following these guidelines ensures that contributions are in line with project standards and are reviewed efficiently. Here's an example. You can find the contribution guidelines in the official Python PyTorch GitHub repository in the contributing.md file. Steps for contributions. Fork the repository. Start by forking the PyTorch repository to your GitHub account, which gives you your own copy of the codebase to work on. Next, create a branch. Create a new branch for each contribution. This keeps your changes isolated from the main repository and allows for easier collaboration and review. Code and test. Make your changes, write test, and ensure your code passes all existing tests by running the test suite. Submit a pull request or PR. Once your changes are ready, submit a pull request to the PyTorch repository for review. Navigating the PyTorch codebase. Overview. The PyTorch codebase is large and well organized with different directories corresponding to various components such as core tensor operations, neural network modules, and distributed training tools. Understanding this structure is crucial for making contributions. Example, Torch contains the core functionalities of PyTorch such as tensors, autograd, and utilities. Torch.nn contains modules related to neural networks, including layers, loss functions, and optimizers. Torch.distributed contains tools for distributed and parallel training. Documentation. PyTorch documentation is extensive, and understanding it is key to contributing effectively. The code base also includes doc strings and inline comments that explain how various parts of the framework work, contributing bug fixes, documentation, and new features. Contributing to PyTorch can take many forms, from fixing small bugs to implementing new features or improving the framework's documentation. Contributing bug fixes. Bug fixes are often a great starting point for new contributors as they require less domain knowledge and are usually well scoped. To find bugs to work on, check the GitHub issues page where bugs are often tagged with good first issue for beginners. Steps: search for a bug that aligns with your skills, then comment on the issue to let maintainers know that you're working on it. Write a fix, add relevant tests, and submit a pull request. Improving documentation. High quality documentation is crucial for the usability of open source projects. You can contribute to improving existing documentation, writing new tutorials, or adding explanations to under documented sections. Example, if you notice unclear documentation or missing sections in the torch.nn module, you can update the doc strings to contribute a tutorial that explains its usage in detail. Process. Contributions to the documentation are handled similarly to code contributions, where changes are submitted as pull requests. Always ensure that your documentation contributions are clear, concise, and aligned with PyTorch's documentation style. Adding new features. Contributing new features or extending existing ones is more complex and requires a deep understanding of PyTorch's architecture. New features must align with PyTorch's development roadmap and be discussed with the core team before implementation. Steps: propose the feature by opening a GitHub issue or discussing it on the forums. Wait for feedback and iterate on the design. Implement the feature, write comprehensive tests, and submit a PR. Best practices: follow PyTorch style guide, ensure backward compatibility, and include unit tests for all new features. Also document the features in the user facing documentation. Engaging with PyTorch community, forums, mailing lists, and social media. Engagement with the PyTorch community helps you stay updated on the latest development, seek help when needed, and contribute to discussions on best practices and new features. PyTorch forums. The PyTorch forums are the central hub for community discussions where users and contributors ask questions, share insights, and discuss bugs or feature requests. Here is the link: https://discuss.pytorch.org. How to engage? Ask questions. If you are working on a challenging problem or need clarification on specific PyTorch features, the forums are a great place to seek help. Answer questions. Contribute to the community by answering questions and helping others solve their issues. Participate in discussions. Join discussions about upcoming releases, research papers, or new features. PyTorch mailing list. PyTorch mailing list allows for more formal announcements and discussions about development, progress, release cycles, and important updates. They are useful for staying informed about larger developments in the project. How to subscribe? Mailing lists are often linked directly from the PyTorch's website or the GitHub repository. Social media and events. PyTorch has an active presence on social media platforms like Twitter, where announcements about new features, tutorials, and community events are shared. Follow official accounts. Following PyTorch's official Twitter account and engaging with the post is a great way to stay up to date. Conference and meetups. PyTorch related talks and workshops are featured at major conferences such as NUR IPS, CVPR, and ICML. Participating in these events allows you to meet other PyTorch users and developers. That's the end of our section. If you have any questions on whatever we have done in this particular video series, please reach out to me using the comments, or you can email me directly at my email at vivianarana@gmail.com, and I'll get back to you as soon as possible. Thank you.